2 capacitors, and 2 switches. The electric circuit includes 1 battery, 2 capacitors, and 2 switches. The battery voltage is 120 volts. The capacitors have capacitances 9 microfarads and 18 microfarads. Initially, all the switches are open and the capacitors are uncharged. First we'll close switch S1 and determine the charge on the capacitor C1 after a long time. We will then open S1 and close S2. Then determine the charge on capacitor C1 after a long time. For part B, determine the potential difference across capacitor C1 when equilibrium is reached. Switch S2 remains closed, and now switch S1 is also closed. The system reaches equilibrium. How much extra charge flows from the battery? When switch S1 is closed, current will flow through C1. You're charging the capacitor like this, right? This switch is open, so no current goes over there. And current will flow until the difference in potential between the battery and C1 is 0. This occurs after a long time, where T is equal 10 times the time constant. At this time, the voltage from the battery will equal the voltage across C1, which is 120 volts. So to find the charge, it's just C delta V. We substitute in the values for the capacitance and the voltage, and we get the charge on capacitor C1 is 1.08 millicoulombs. We open switch 1 and close switch 2. We want to find the charge on the capacitor C1 after a long time, and another way of saying that is you're at equilibrium, or the time equals 10 times the time constant. So what's going to happen here? The battery's out of the circuit, and the capacitor was charged like this, plus on the top, negative on the bottom. So charge will flow. The capacitor acts almost like a battery there, providing current. C1 starts with a potential of 120 volts, and C2 has 0 volts. The current will flow until delta V between the two capacitors is 0. Due to conservation of charge, the final charges on each capacitor must sum up to the original charge that we found in part B. We'll use prime notation to denote the final charge and also the voltage difference on each of the capacitors, with Q equal 1.08 times 10 to the minus 3. Again, that was from part A. That's the total charge that has to be shared between these capacitors. So we've opened up switch 1 and closed switch 2. Current will continue to flow until the potential drop across C1 is equal to the potential drop across C2, equal and opposite. So that's what's reflected here, which tells us that the two voltage drops have to be the same, so that's going to be one initial condition, and the total charge that we found earlier will be split between the two capacitors. So now we move up over here, and this first thing, this is just the delta V1 prime equals delta V2 prime, where we replace delta V with Q over C. The next step is to get rid of a variable. We don't want to know the charge on capacitor 2, so we don't really need this, but what does that equal to? Well, that's just the total charge minus Q1 prime. So let me erase some of this stuff so you can take a breather. There's a lot going on here. And what do we do now? Now we're just going to do some algebra, okay? So we take this guy and this guy, set them equal, move some letters around, and we keep doing it over here. So please work that on your own to make sure I'm doing this right. And finally, we get Q1 prime is equal to Q, which is the total original charge, times C1 over C1 plus C2. We substitute in our values, and we find that the new charge on C1, this guy right here, is going to be 3.6 times 10 to the minus 4th coulombs. Now we would like to find the potential difference across capacitor C1 when equilibrium is reached. We just use our equation for the potential difference. That's just Q1 prime over C1. We found Q1 prime on the last slide. We were given C1, and we come up with a potential difference of 40 volts. Switch S2 remains closed, and now switch S1 is also closed. How much extra charge flows from the battery? After equilibrium is reached, we now have a potential difference of 120 volts across C1, across C2, and of course the battery. This means the difference in potential between the capacitors and the battery is zero, so no current flows, so we're in equilibrium and they are now fully charged. C1 will go back to its original charge, right? Because Q is just equal to CV. We're back to the original 120 volts. So our initial condition in part A had 1.08 millicoulombs. So that's back. That's all back right on this guy. However, C2 is now going to be able to store charge. So the extra charge that flows from the battery will appear totally on C2. The extra charge will be the charge that winds up on C2, as C1 just goes back to its original total amount of charge. So delta Q extra will equal C2 times the voltage difference across C2, which is 120 volts. The capacitance is 18 microfarads, so the extra charge that comes out of the battery is 2.16 times 10 to the minus 3 coulombs.